Hello AP Calc. This video should be very helpful to you for 6.2. It's all about it's titled like they're motion problems where we're dealing with position function, velocity function, and acceleration. So I'll try to reduce my loquacious behavior today so that you guys can become more perspicacious as it regards to calculus. So the first thing I need to talk about is how position relates to velocity, which relates to acceleration. So first things first, let's just think about the kind of units that we would use to describe each of these phenomena. Position. This just means from a standard starting point, how far away are you from it? So meters, feet, something like that. So let's say we're talking meters. Velocity. That'd be something like, meters per second, miles per hour, feet per minute, whatever. I'm just going to go meters per second. Acceleration's one where a lot of people don't really, off the top of their head, know how to describe acceleration. It's the rate at which your velocity is either increasing or decreasing. So it's think about this. So let's say we're in our car. We're 20 meters from our home. And we're traveling 55, well, I'm trying to think of miles per hour now. Let's switch it from meters to miles. We're 20 miles from our home. We're going 55 miles an hour. But somebody hits the acceleration a wee bit. And let's say we're increasing to 60 miles an hour and 65 miles an hour. We're on the interstate where it's legal. We are saying, hey, you're increasing this many miles per hour. So it's kind of like, think of it as like a race, a sprinting race. As the person accelerates, their velocity, their meters per second can either are increasing per second. So the way, sorry, I'm talking around in circles. Acceleration is meters per second, which is otherwise known as meters per second squared. It's kind of like this idea of if I take a fraction divided by a whole number, the whole number flips and you multiply, so there's a second on the bottom. So, think about this. It's a rate of change, slope, right? Change in y over change in x. Y would be meters, x would be seconds. Then we got another rate of change here. These are rates of change of one another. So, if this is the function f, to get to velocity, you do its rate of change. To get to acceleration, you do its rate of change. So, position oftentimes is represented by s of t. The velocity is v of t, and the acceleration is a of t. But it's under this understanding that, velocity is also known as s prime of t. If I take the derivative of position, I get the velocity. And then if I take the second derivative of position, I get the acceleration. So there's the overarching relationship between position, velocity, and acceleration. If I take derivatives, I can move down from one unit to the next. So with that in mind, can we make sense of this? So you're given a position function. Looks like it's a cubic one. Now, let's say that this position function pretty much is just talking about, here's the origin, and you're either moving away from the origin or you're moving towards the origin. Because I think that makes a little more sense in terms of like driving a car, right? You're either getting closer to that origin or you're going further away from it. And we could say like, hey, this direction's positive and this direction's negative, or that direction's positive and that direction's negative. We'll keep it simple by just saying, point in the origin, we're just going to slide horizontally back and forth. If this is your position, and you can't go below 0 for time, how do you find the velocity of the particle after 1 second? Well, we just talked about how the velocity is the first derivative of the position function. So we're going to take the first derivative. Just power rule for each one. Bring the power down, subtract. And then this is the same as velocity, and then I'm going to plug in 1 second. Those go in for the t's. So you get 15 minus 6, which is 9, minus 21, it's negative 12. So if we were just talking in terms of here's the origin, we're going left. We're traveling left. Not necessarily that we are left of the origin, we're traveling left. And we would use the correct unit, feet in terms of seconds, so feet per second. Now, negative is important for velocity because it represents the direction that the object is traveling. Is the particle moving to the left or to the right at that moment? We know it's going to the left. That negative is pointing us in that direction. What's the position of the particle at this time? Great question. Well, here's my position function. The time in question is 1 second. So all I got to do is plug in 1 for my position for all the t values. So this would be 5 minus 3 minus 21. So it's at negative 19 feet. So what? What? The position of my particle is negative 19 feet. So that means 19 feet left of the origin. All right, so I'm going to try to keep some of these things in tow. We had 5t cubed minus 3t squared minus 21t. This was our position. I know I'm probably off screen right now. Don't worry about it. Our velocity was 15t squared minus 6t minus 21. And now we're being asked a question about acceleration. So the acceleration of it is the second derivative. So take the derivative of the velocity. You take the derivative of the velocity, and you're going to get acceleration. So 30t minus 6 would be the acceleration. So 1.1 is what we would plug in to determine the acceleration at 1.1 seconds. Quick math, 30 times 1 is 30. 30 times 0.1 is 3. So it's 33. All right, 27 feet per second per second. So feet per second squared for velocity. And I guess that's all I asked for part B. Looks like I gave you a lot of space there. All right, now I'm going to erase everything here. Go on to our next unit. this is the part that requires well, maybe some in-depth explanation. So I've got my position function. Describe the motion for the particle, including where it speeds up, where it slows down, where it stops. And I'm actually going to draw a graph of the situation because I think you had to do that through the reading material. I just want to show you guys what that looks like. So first things first, we can talk about where a particle stops because I think this makes the most sense. A particle would stop when the velocity equals 0. Right. So my velocity is the rate at which my position is changing. When my position stops changing, that means that the velocity is 0 feet per second. So we just got to find the solution for when the velocity equals 0, and we've got the places where it stops. Sorry, I don't think you could see the whole thing. So that'll be my first task. 0 equals 15t squared minus 6t minus 21. So you know what? I'm just going to plug it into the quadratic formula my nifty calculator has. 15, negative 6, and negative 21. So I got negative 1 and 1.4. Turns out it's factorable. Now the negative 1 you can toss out because we're talking t is greater than or equal to 0 here. Time's not going to go negative. So it stops at t equals 1.4 seconds. So what about this whole speeding up versus slowing down? Well, here's where things get interesting. Think about the velocity and think about the acceleration functions. So velocity equals 0 at t equals 1.4. You can think of that as a critical number for the position function. So here's 0. We're going to say this is velocity. This is going to be acceleration. 1, 2, 3, 4. And it has no stopping point, so it really is open-ended here. But if this is 1, 2, 3, 4, 1.4 right here on the number line is a critical point. It stops here. Similarly, the acceleration is going to be a point of interest where that equals 0. 30t minus 6 was the acceleration function, so 6 divided by 30 is going to be 1/5. So t equals 1/5 right here is going to be the place where the acceleration is 0. Okay? So this is v of t equals 0. This is a of t equals 0. And here's what we do. We treat them as if they are intervals by which to test increasing versus decreasing. Okay? Here's why. When the direction of velocity matches the direction of acceleration, either both going positive or both going negative, that's a sign of speeding up. Okay? So this particle speeds up when both velocity and acceleration share the same sign. When velocity and acceleration have different signs, they slow down. Well, yeah, they slow down. So what we do is we say, pick a number in this interval right here for velocity. So something less than 0. Plug in 1. What's the velocity function? 15t squared minus 6t minus 21. You plug in 1 here, and you're going to get negative 12. So it's kind of like saying, hey, we're negative, 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 from 0 to 1.4. From 0 to 1.4, our velocity is always negative. Plug in a number bigger than 1.4, like 2, and you get something like 60 minus 12, which is 48 minus 20. That's going to be positive. So the velocity is always positive here. So it's like this. Particles moving left. Particles moving right. Do the same thing now with acceleration. Give us a number that's less than 1/5. So, and it can't be 0, right? It's got to be something like 1/6, right? 1/6 times 30 is 5 minus 6. It's negative. So it's negative here. Negative, 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 negative. After that, the acceleration is positive. So here's how you read this, here's how you interpret this situation. From t equals 0 to t equals 1.4, you're speeding up because the velocity and acceleration share direction. And from 1.4 to infinity, or t is greater than 1.4, you're also speeding up. Same sign speeds up. Same sign speeds up. Between 1/5 and 1.4, they are different signs. Negative, positive. That would indicate slowing down. And you know what? Just for time purposes and where we are in the semester, I'm not going to draw the path that the particle takes. So, wow, 18 minutes in. We're going to leave it at that for this video, and then I'm going to probably come back and talk about how to determine the maximum speed and how do we deal with those weird graphs that they give us and how to determine, hey, here's the position function. Is it speeding up or slowing down? That kind of thing. See ya.